Hi, this is John Whitaker, and this is our 34th video for the Mathematical Analysis 2 class. And we ended last time with Abel's theorem, and today I want to start off by doing something I'm going to call a corollary that's proofs based on Abel's theorem. And it's a statement that we've made before. And so, just as a comment, we previously stated this theorem. But did not prove it. Okay, here's what it says. It says, if the summation is n runs from 0 to infinity of a sub n, the summation as n runs from 0 to infinity of b sub n, and the summation as n runs from 0 to infinity of c sub n converge to a, b, and c, and if the c sub n's, let me write it down here, are equal to a sub 0, b to the n plus a sub 1, b to the n minus 1 plus a sub 2, b to the n minus 2 plus all the way up to a sub n, b to the 0, then c is equal to a times b. Okay. Proof, we let the sum as n runs from 0 to infinity of a sub n equal to a, the sum as n runs from 0 to infinity of the b sub n is equal to b, and the sum as n runs from 0 to infinity of the c sub n is equal to c, where the c sub n's are equal to a sub 0 bn plus a sub 1 bn minus b sub n minus 1 plus all the way up to a sub n b to 0. And now what we're going to do, first, self-the situations, use Abel's theorem. We're going to define f of x being equal to the sum as n runs from 0 to infinity of a sub n x sub n, and g of x to be equal to the sum as n runs from 0 to infinity of b sub n x sub n, and h of x to be equal to the sum as n runs from 0 to infinity of c sub n x sub n for 0 less than or equal to x less than or equal to 1. This is a comment. We know we can make such definitions, okay, because in the proof of Abel's theorem, okay, we show these sums were convergent for what we shown was for the absolute value of x being less than 1. Here we're just going to use from 0 to 1, but we could have negative x values. Now, for 0 less than or equal to x less than 1, we have each of these power series converging absolutely as a convergent power series converges absolutely in its radius of convergence. So for each x n, we'll say 0 to 1, due to the absolute convergence of these series, we have the sum as n runs from 0 to infinity of a sub n x n times the sum as n runs from 0 to infinity of b sub n x sub n is going to be equal to a sub 0 x sub 0 plus a sub 1 x sub 1 plus a sub 2 x squared plus and forever times this b sub 0 x sub 0 plus b sub 1 x sub 1 plus b sub 2 x sub 2 plus forever, which we could rewrite as a sub 0 x sub 0 plus b sub 0 x sub 0 plus a sub 0 x sub 0 b sub 1 x sub 1 plus a sub 0 x sub 0 times b sub 2 x squared plus, we keep going on forever in this fashion, plus a sub 1 x1 b sub 1 x1. I think this should be b sub 0 x 0, that's right. Plus a sub 1 x1 b sub 1 x1 plus a sub 1 x1 b sub 2 x2 plus, and keep going forever, plus here a sub 2 x squared times b sub 0 x sub 0 plus a sub 2 x squared b sub 0 b sub 1 x sub 1 plus a sub 2 x squared b sub 2 x sub 2 plus forever. And then if we just add them according to the powers of x, we could have a sub 0 b sub 0 plus a sub 0 b to the 1 plus a sub 1 b to the 0 times x to the 1 plus a sub 0 b sub 2 plus a sub 1 b sub 1 plus a sub 0 b sub 2 x squared plus, and forever in this direction, and that's equal to the sum as n runs from 0 to infinity of c sub n x to the n. Thus, what we have in terms of our functions is we have f of x times g of x is equal to h of x. And that's true for all x element for 0 to 1 in this fashion. Let's open here to the right. So by Abel's theorem, what we have is that the limit as x goes to 1 of f of x, that's going to be equal to a. The limit as x goes to 1 of g of x, that's going to be equal to b. And the limit as x goes to 1 of h of x, that's going to be equal to c. Okay? And so, the limit as x goes to 1 of, well, I should say this. So c equals to the limit as x goes to 1 of h of x, which equals to the limit as x goes to 1 of f of x times g of x, because that's what h of x is, which equals to the limit of each one of these guys. Which equals to a times b, and that's the proof. Okay. All right. We're going to kind of look at what we did in that previous corollary a little bit and have a theorem about it's kind of rewriting the summations. And here's what it says. It says, given, rewriting the order of the summation, given a double sequence, we'll say a sub ij, where I is equal to 1, 2, 3, forever, and j is equal to 1, 2, 3, and forever. Suppose that the sum, as j runs from 1 to infinity, of the a sub ij's equals to b sub I and the sum of the B sub i's convergence, then the sum as I runs from 1 to infinity, the sum as j runs from 1 to infinity of A sub ij will be equal to the sum as j runs from 1 to infinity, the sum as I runs from 1 to infinity of A sub ij. That's the theorem, and pretty much used that in the previous work, that corollary. A way of understanding this is this theorem is stating that if you have an array of numbers, and this is infinite array, and here we have A11, A12, A13, A14, so forth, and A21, A22, A23, A24, and so forth, and A31, A32, A33, A34, and forever, and A41, A42, A43, A44, and forever down, like this. Then what we can say is that summing under these conditions, okay, summing the sum of each row. So if you take this row, add it to whatever this row's sum is, to whatever this row's sum is, equals, okay, the sum of each column. That is, you take this plus this column's answer plus this column. So that's what we're going to do. So here's the proof. We let A sub ij, where I is equal to 1, 2, 3 forever, and j is equal to 1, 2, 3 forever, be a double sequence. Sequence that depends on two indices. And suppose that the sum of the j, as j runs from 1 to infinity, of the absolute values of the A sub ij equals to bi. Then, and this is true for, I'm sorry, not then, but for I equal 1, 2, 3 forever. Okay? And that the sum of the bi, as I run from 1 to infinity, converges. We want to show that the sum as I runs from 1 to infinity of the sum as j runs from 1 to infinity of the aij is equal to the sum as j runs from 1 to infinity of the sum as I runs from 1 to infinity of the aij's. Well, what we're going to do is we're going to do this kind of in a very constructionist type way. We're going to consider the set E equaling to the singleton 0 plus, or union, the set of objects 1 through n, where n runs from 1 to infinity. Okay, this set E is countable, and we will label its points by x of 0 equals to 0 and x of n is equal to 1 over n, or n equals 1 to. Okay, that's what we have. Okay. Now note, x of 0 is a limit point of E as the limit as n goes to infinity of x of n equals to x of 0, 0. Okay. We define f sub I of x naught equals to the sum as j runs from 1 to infinity of a sub ij, which converges because the sum as j runs from 1 to infinity of a sub ij is absolutely convergent. For each fixed I. Now we're going to define f sub I of x of n, any other point in E, equal to the sum as j runs from 1 to n of a sub ij, and, wait just a second, yes, that's what we're going to find, and we're going to find g of x to be equal to the sum as I runs from 1 to n, I'm sorry, 1 to infinity this time, of f sub I of x. And that's for each x element of E. And I should say where we know that this sum as I runs from 1 to infinity of f sub I of x exists for all x in E. Let me show that justification. Because sum as I runs from 1 to infinity of the absolute value of f sub I of x is going to be less than or equal to the sum as I runs from 1 to infinity of the absolute value of the sum as j runs from 1 to whatever, depends on the x here, of a sub I j, which is less than or equal to the sum as I runs from 1 to infinity of the sum as j runs from 1 to whatever of the a sub I j. Remember, this is equal to the b sub i's, so this is less than or equal to the sum of the b sub i's which converge. So that is absolutely convergent, so that's why g of x is well defined. We wish to show for each fixed x for each fixed I, f sub I is continuous at x naught. Okay, that's 0. Okay, so let epsilon be greater than 0 be given. We need a delta bigger than 0 such that f sub I of x minus f sub I of x naught will be less than epsilon for all x in E with, here, the norm of x minus x naught being less than delta. Okay. For x equal to x naught, f sub I of x minus f sub I of x naught, well, that's going to be equal to 0, which is definitely less than epsilon. So any delta will work. So that doesn't put any restrictions on our delta. Okay, so we're going to have to worry about the other types of x's. Now note, f sub I of x sub n, the other types of x's, minus f sub I of x naught, will be equal to the sum as j runs from 1 to n of a sub I j minus the sum as j runs from 1 to infinity of a sub I j. Now, since the sum of the a sub I j as j runs from 1 to infinity inside absolute values converges to the b sub I for each I, then there exists an n, a natural number, n, now it depends on I here, and we'll say greater than or equal to 2, such that for all n greater than or equal to big N, the sum as I runs from 1 to n of a sub I j minus the sum as j runs from 1 to infinity of a sub ij, that's going to be less than epsilon. Okay? That's because with the a sub ij's being absolutely convergent, as j runs from 1 to infinity, then the a sub ij's, the sum of the a sub ij's are convergent, and that's what gives us this. So we let delta be equal to 1 over n minus 1. So for all x in E with x sub n minus x sub 0 being less than 1 over n minus 1, that's our delta, we have, well, here, this is going to be 0 to x sub 0, and x of n is 1 over n, so that's just 1 over n is less than 1 over n minus 1, big N minus 1 here. Okay, so that says that n minus 1 is less than n, or that n has to be less than or equal to n. Okay, little n. And so for all x in E with x minus x of naught being less than 1 over n minus 1, the f sub I of x minus f sub I of x naught will be less than epsilon. Thus, that shows that f sub i's is continuous at x of naught, and that's for each I. Okay? All right, now, since the f sub I of x inside absolute values here is equal to the sum as j runs from 1 to n of a sub ij, which is less than or equal to the sum of the absolute values of a sub ij, as j runs from 1 to n, which is less than or equal to the sum as j runs from 1 to infinity of the a sub ij's, which we know is equal to the b sub I, converge, for x different than x naught, and f sub I of x naught is equal to the sum as j runs from 1 to infinity of a sub I j inside absolute values, which is less than the sum of the a sub I j's absolute values of them, as j runs from 1 to infinity, which equals to the b sub i's. Then we're going to quote a previous theorem here. Use a previous theorem. Well, we have at this stage that f sub I of x inside absolute x is less than or equal to b sub I, and that's true for every x element of E. And for all the i's equal 1, 2, 3. So since the sum of the b sub i's converge, Then by a previous theorem, the sum of the i's run from 1 to n of f sub I of x converge uniformly to g of x for all x element of E. Okay. Since I'm going to define this, each term in here, I'm going to denote it by g sub n is equal to g sub n of x equal to the sum as I running from 1 to n of f sub I of x is continuous. Now we show each one of these guys is continuous at x sub naught. And so a finite sum of continuous functions at x sub naught is going to be continuous. And g sub n converges uniformly to g, then that'll imply that g is continuous at x sub naught. This continuity is by a theorem that we've done previously. And it generated a kind of a more general theorem than what I'm just using here that said that if your sequence of functions are continuous and they converge uniformly, what they converge uniformly to is continuous. Okay? But I'm going to write up a little bit more of an explanation here. I'm going to say this is true because by a previous theorem, where we have the limit as x goes to x naught of g sub n of x equaling g sub n of x naught. That's true because of continuity of g sub n at x naught. And the limit as n goes to infinity of g sub n x naught is equal to g of x naught. Then the limit, I'll write it down here, as x goes to x naught of g of x is equal to the limit as n goes to infinity of g sub n of x naught, which equals to g of x naught. And this part, this limit as x goes to x naught of g sub x equaling g sub x naught, where x naught is the limit point, is what gives us the continuity of g at x naught. Okay. Thus, this sum as I runs from 1 to infinity of the sum as j runs from 1 to infinity of a sub ij equal to the sum as I runs from 1 to infinity of f sub I of x naught is equal to g of x naught, okay, and that's equal to the limit as n goes to infinity of g of x sub n. That's due to the continuity. This equality comes from the continuity of g at x naught which equals to the limit as n goes to infinity of the sum as I runs from 1 to n of f sub I of x sub n, which equals to the limit as n goes to infinity of the sum as I runs from 1 to infinity. Here, I mean, just wait just a second. This should be I runs from 1 to infinity here, of the f sub I, x sub n. And here, this is the limit as n goes to infinity. The sum as I runs from 1 to infinity of, here the f sub I of x n is nothing more than the sum as j runs from 1 to n of a sub I j. This is just following the definitions of our functions involved in the proof. Most of it, that's what's involved. Which equals to, finally, the limit as n goes to infinity of the sum as I run from 1 to infinity. I'll write down as a sub I1 plus sum, a sub I2 plus a sub I3 plus all the way up to a sub In. That's finite. And so what I'll say is, note, for a fixed j, that the sum of the absolute value of a sub ij is less than b sub I for each I. And the sum, as I run from 1 to infinity of b sub i's converges. Thus, that gives us that the sum as I runs from 1 to infinity of a sub I j, okay, converges for each fixed j. Okay, so we have that the sum as I runs from 1 to infinity of the sum as I runs, j runs from 1 to infinity of a sub ij, which equals to this limit as n goes to infinity of what I just written up there at the top of the board. Sum as I runs from 1 infinity of a sub I1 plus a sub I2 plus all the way up to a sub ij. Look, we're saying each one of these guys as a sum, the summation of each one of these as I runs converges. And so we had a fact that if you add two convergent sums, that's the same thing as the sum of the first plus sum of the second. So here we can extend that to be equal to the limit as n goes to infinity of the sum as j runs from 1 to n of the sum as I runs from 1 to n of a sub I j, and as n goes to infinity, this becomes the sum as j runs from 1 to infinity of the sum as I runs from 1 to infinity of a sub ij. And that's what we were trying to prove. So we can rearrange the way that we add things in this fashion. Okay. Ladies and gentlemen, I'm going to call it quits there. We went over last time. And so thank you very much.